All right, one of the last topics is atomic physics. And this is just stuff about energy levels in the atom and other considerations that are similar to those. Really, we want to talk mostly about the hydrogen atom. It's easy. It's got one electron orbiting one nucleus, and we understand Coulomb's law for that very well. And really, it doesn't have to only be hydrogen atom. It could be anything that's hydrogen-like. And what does hydrogen-like mean? That's helium plus, lithium 2 plus, beryllium 3 plus, and so on. Anything that has a nucleus, but only one electron that goes around it. We'd like to focus our attention on the hydrogen-like atom because, well, one, it's easy, and two, a perfect, true solution for the helium atom doesn't exist. We don't have computers that are sophisticated enough to do it. The physics is very complicated, and it comes from the interaction, the time-dependent interaction between the two electrons as they go around. We need to know where they are and what they're doing at all times. Whereas for the hydrogen atom, we can make an energy argument at all times. We talked a little bit in the past about issues of modeling, right? I think that was back in Gauss' law where we said the atom is a point. No, now it's a sphere. It's a solid sphere, it's a shell, and we came up with different kind of schemes. This is how we really do try to solve the helium atom in physics, is make a model, test it out, make some approximations, and try to get it as close to experiment as possible, and add more and more corrections to the model, but at least it's doable because an exact solution is not. All right, we could derive quantum physics in about 20 minutes with a couple of just assumptions. One of them would require knowing that the electric field is zero inside a metal and knowing that photons are made of electric fields. And another one is recognizing that matter actually has wave-like properties. So when we dealt with the photoelectric effect, I think you discovered that, hey, photons exist. So light is a nice continuous wave, but it also is a very discrete kind of particle-like nature. It turns out that massive bodies also have the same kind of thing. It's called the de Broglie wavelength. And I think it's as simple as just h over p. If I'm wrong about that, I'll correct it in editing. So that means that anything that has a mass, as long as it's got a momentum, mv, it has some kind of associated wavelength. And that means technically, near the end of the semester, we're in the studio room and we've got two possible doors. And here I am about to lose my mind and go screaming out of here, right? So I'll give myself those crazy fish eyes. I'm angry, I'm about to lose it, and I come screaming out of one of these doors and just take off. Well, technically, at the very edge of the universe, far, far, far away, it turns out I was diffracted a little bit by some angle. And it comes from the nature of, I have a wavelength because I'm a wave-like in nature. And here's two slits. That's a double slit experiment. So diffraction matter waves is a real thing. So that's going to be our take home. Massive particles do interfere. They interfere, they diffract, they do all of these things. So that's weird. And then also, of course, we know there's a background to this. Light is also a particle. So there's kind of this duality between waves and particles. So light's a particle by photoelectric, photon, and then massive particles are waves. And this connection is something that you'll talk about in Physics 3. Realistically, are you expecting to see me diffract? No, because my wavelength's going to be pretty close to zero. My mass is going to be enormous compared to 6.636 times 10 to the minus 34 joule seconds. So for a very large macroscopic body, forget about it. You're not going to see it. But for individual electrons, we do. It was a very famous experiment in the 20s where Louis de Broglie, a French grad student, just shined some electrons on crystal and got a beautiful diffraction pattern that came out. And it's like, well, that's weird, right? Because what's the thing that's diffracting? The electrons themselves have a wavelength. The crystal planes of the atoms in these crystals make slits, and then we saw diffraction. So for reasons that may become complicated, let's just talk about doing confinement of an electron as it goes around an atom. So let's say this is its orbital radius. And let's say it starts here. And we said that as this thing goes around, remember, it's got a wavelength. So that means that it's got an amplitude that's up, it's down, it's up, it's down, it's up, it's down. And we have a real problem here. If these don't agree at the same point, then we don't have the closed loop, and we've got problems. There should be a standing wave as the wave goes to one boundary and then reflects back off. This is a case where there's no boundary, but as it travels, it should set up a standing wave pattern, and this is just something that's not really allowed, right? It would have to come to some kind of nice standing wave. So that means that we expect to see something that maybe looks more like this, right? If it starts out, maybe we get 1 and 2, right? That'll be the first node and the second node, or the up and down antinodes. Or maybe you have something that looks more like this, right? You know, something that's closed and has fixed amounts of nodes and antinodes. That's interesting because that shows us that the wavelength is quantized, which is a fancy word of saying, a way of saying it's not continuous, right? For wavelengths, and really this is related to energy and momentum also. So all of these things are quantized. So instead of having a smooth continuum like you just crawling up a hill and you can take any MGH you want, we find out that the energy occurs in steps because of this quantization. I can be at 3 MGH, I can be at 5 MGH, but I'm not really allowed to be here at 3.5 MGH. My potential energy has to take discrete values. Okay, so this is a condition that we call energy quantization. And it's a direct consequence of imposing boundary conditions. The fact that I require these to be the same gives us a quantized wavelength, which in turn gives us quantized energies. Okay, so what's going on inside the hydrogen atom? We've got a potential energy well that looks like this. And where do these potential energies come from? They're really kind of related to the voltage due to a charged particle. We've got the nucleus is pulling on the electrons. We know that the voltage is related to 1 over R. And we know that the potential energy is related to Q, or the electron, times the voltage. So if we know that the voltage is quantized, or the allowed energies are quantized, then that means we have a very fixed specific equation for the allowed energies. And they are related to a bunch of constants that I don't remember off the top of my head. And why? Because we don't use them. All right, we've already done that work up front and found minus 13.6 EVs are related. And then they're divided by this number n, and n is what we call the principal quantum number for the system. It's becoming unreadable, 1 over n squared. Really, I can kind of cheat a little bit if this was hydrogen-like. So what's the only difference? I have a more dense nucleus with more charge. It would pull a little bit harder, depending on how many protons are in that nucleus. So really, we could modify this and make it hydrogen-like as minus 13.6 EVs times z squared, and that's the number of protons in the nucleus over n squared. Okay, so inside this model, what does that mean? Whoops, what does that mean that we can see? I've got energy levels at different positions. And I say positions as in positions in this energy well. This would be the n equals 1 state. The 2 is a little higher. The 3 is less high. The 4 is less high. And we notice that as we climb, these get closer and closer together. And of course they should, right? 13.6, whereas over 1 is minus 13.6. That's pretty deep. But then the next one would be over 2 squared. That's only a quarter as deep. And then a ninth is deep, and a 16th is deep, and so on and so on. So as we get closer to infinity, we get less and less negative numbers that are closer to what we call the continuum, and that's the ionization threshold of getting out. All right, so what else should we say? Let's make this problem hydrogen. So this is hydrogen. That means that Z is equal to 1, and we want to use the original equation. Realistic kinds of problems that we might ask you about, talk about issues with the electron doing transitions. So let's say that we have an electron in the ground state, and somehow I kick it and elevate it up here into the n=4 state. The universe doesn't like high energies, right? So it would naturally want to fall, just like you balancing a ball on top of a table or something. It wants to roll off. So it has options. It can decay into the n=3 state. It could potentially come down here into the 2 state, or it can come all the way down into the 1 state. There are just a lot of options for this electron to fall back down to a lower energy state. And a question would be, what happens to that energy? We started here at E4, which is not very deep, and we wanted to land at E1, which is really deep. What do we do with all that extra potential energy? We have to get rid of it somehow. So what the electron will do is bundle it up in a photon and then emit it. So here comes some change of energy in the form of a packaged up photon. The photon has an energy, and the photon therefore has a wavelength associated with that energy. So in the lab, what we would do is measure the wavelength. So some questions that I might ask, here's one that we'll do in the lab. It says measure predict the wavelengths of all transitions in the Balmer series. So what happens here is that all transitions that end in 1 are just specially named, right? An electron going from 2 to 1, from 3 to 1, 4 to 1, 5 to 1, all of these possibilities that all end in n=1 is just called the Lyman series. All of them that end in number 2 is called the Balmer series. All of them that end in 3 is actually called the Paschen series. And then after 4, we step in and say, hey, you can't name every one of these, so we just put a stop to that, right? I mean, there is an associated series with every other final state, but they're not special enough to be named because this is becoming absurd. So we'll ask you, find all the ones in the Balmer series that are maybe visible, and the way to do that is fairly straightforward. Let's say I wanted you to measure the wavelength for a particular transition, and let's say we're coming from 4, and we're going to decay, let's say, into 2. We would find the final energy is E2, which is minus 13.6 EV over 2 squared. All right, so that's a number. We would find the initial energy that started out at E4, or minus 13.6 EVs over 4 squared. And then you need to find what's the difference in the energy. What's the change? It'll be E final minus E initial. I don't have that answer, so do that on your own with a calculator. Some things to note. What if the change in the energy is negative? The interpretation is energy was released. Is that reasonable? Of course it is. This is a negative change in energy. You're going even deeper. The atom is losing energy, so that means the photon is carrying it away. This is emission. So atoms that are doing this are glowing and showing us their spectral fingerprint. If we wanted to do this and we found out that it was positive change, that means energy is coming into the system, or that's an absorption. The last thing that you need to do to find out what the wavelength of this is just say, okay, this is the amount of energy that we're dealing with. Put it into a photon. What color is it? We'll say the change in the photon energy is related to E photon, which is hc over lambda. Let's say, I didn't do the math, but let's say that we got an answer in this case of maybe minus 500 nanometers because we had a negative energy change here. This is absurd. There's no such thing as a negative wavelength anything, right? The number is the wavelength. The minus sign is just something that we had up here that told us the energy came out. So you should never be reporting wavelengths in terms of negative numbers. It just doesn't make sense. Make a note. Okay, if it was negative, that's an emission. If it's positive, it's an absorption. And then solve for the number. It's all about absolute values of what's the energy that was absorbed or released. Okay, what's interesting about these is that every single atomic or molecular species has a unique energy level diagram, right? And when we talk about hydrogen, that's minus 13.6 eV over n squared. If we're talking about helium, let's say helium plus, well, that's going to end up being minus 13.6 eV times 4 over n squared. So all of these energy levels are going to look a little bit different, right? In the hydrogen case, let's say that they were these. In the helium case, these are going to be even deeper. The helium starts way down here, and then its levels are just different. And what's that mean about the transitions that are allowed, right? These kinds of transitions emit their own wavelengths. These are completely different numbers of energies, right? So their wavelengths are going to be different. So what we would do in atomic spectroscopy, look at a sample that glows, run the light from it through a diffraction grating, and then we see the individual wavelengths are spread out. And that gives us a graph, right? Or a plot of different lines at different wavelengths. I just made up some numbers. So then we put an army of grad students to work in building the Handbook of Chemistry and Physics and just cataloging all of these. So that if you have a mystery sample, you run it through a light, you look for hallmarks and say, well, you know, this kind of corresponds to this particular color and this species. So, you know, this could be indicative of all of these possibilities. And then when you find the next one, you say, well, now we've eliminated more, and we keep honing down until we find out what is inside the sample, right, based on that. It's a really useful tool for astronomers. You can just look at light through a telescope. How do we know that planets have oxygen in their atmospheres? You look at the atmospheres, right? Literally just run their atmospheres through diffraction grating and see, is diatomic molecular hydrogen or oxygen present? It's got a fingerprint. Nothing else has that exact combination of lines. So proof positive, you've got hydrogen or oxygen. Same thing goes on in the sun. It's a full rainbow for a lot of heat reasons. All the photons that come out are very well understood, except there's a few absent bars that correspond exactly to hydrogen 1. And it's because most of the sun's atmosphere is hydrogen. Those particular wavelengths happen to be the magic ones that cause absorptions in the atoms, so they're quickly sucked up and taken out of the spectral fingerprint of the sun. So it's a useful, non-invasive method to kind of gauge what is something made of. And it just happens to be that everything has its own fingerprint, and it's there ready to be collected.